Of course. Let's do it. Yeah.
Yeah. Okay. Yeah. So good evening. This is our 7th tutorial session on NPTEL course on finite element modeling of welding processes. So in today's session, we will be talking about a little about heat equation, and then we'll also review some of the heat source models that were discussed in the lectures, and also talking about implementation in fenicsx package. So let's just first let me start writing about let's derive let's talk about heat models. I mean, at first let's talk about heat equation, because that forms the crux of the heat of this modeling part in that we are attempting to do infinite element modeling here. So so what I'll do is, let's start with heat equation. And so the way we are going to implement in fenicsx, so I'll just present from that perspective. So let's talk. So say fundamentally, the way we define heat modeling is we'll have rho Cp del T by del T is equal to kappa Laplacian of T plus some source Q, right? So this is where rho is equal to density of the medium. Cp is the specific heat at constant pressure. And T is the dependent variable, which is nothing but temperature field, essentially. Temperature field. Then kappa is our.
This is similar to pressure poison equation, but you have additional time.
Yeah. Right? Yes, that's the thing here. So kappa is what we call as the thermal conductivity of the material, of the medium, or the material. And Q is our heat source. So this is a partial equation, essentially. It's in first order in time and second order in space. So there's also, it will be defined over some domain omega. And for this problem to be well posed, we need certain boundary conditions. And so let's specify some very particular boundary conditions, is that, and since it's first order in time and second order in space, so because of that, we would also require one set of initial conditions, which is meant to start the problem. Then the other set will be the boundary conditions. So initial conditions, you'll have something, say U is equal to U naught. And let us define this omega in general to be so the way we define it is defined omega cross 0, t. T is the final time. And U is U naught, which is nothing but our and it is a function of, say, x vector, and depending on whether it's 1D, 2D, 3D, we'll have x vector as xy, xy, or xyz. And on for boundary conditions,
shouldn't be T. Why are you writing it as U? Shouldn't be T,
okay,
right?
sorry.
T equal to...
Yeah, sorry. Yeah. So it will be T is equal to T naught, right? Yeah. When BCs, for BCs, we would say if you prescribe something on say on the edges, right? So we'll call it D here indicates Dirichlet boundary condition. This would also be, this will be defined on the boundary of the domain cross 0, t, in the sense that we can even have boundary conditions which are functions of time, isn't it? That's the as a general boundary. And we can even have heat transfer per se. But let us leave it for that for the sake of simplicity. We'll just keep it as it is, just for the sake of simplicity. Otherwise, you can have, say, radiation, and say radiation we can have, convection we can have at the boundary, isn't it? And even conduction. But let's keep it as it is as of now. Just let's only consider the Dirichlet boundary condition, right? And this will be at t is equal to 0, right?
Okay.
And Q here can be a function of the domain, I mean, of every pointwise function, and also function of time. It in a very general setting.
And the unit of Q should be time, temperature per something.
Yeah,
per area?
it will be joule per meter cube. Now let's just verify this. I mean, let's just verify this so as to not to. So we have rho Cp partial T by partial T, right? So let's define and let's try to get the unit. So rho will be kg per meter cube, and Cp is usually joule per kg per Kelvin, right? And T Kelvin is, and let's keep it something like that, joule per kg hyphen Kelvin, and then Kelvin by seconds, isn't it? So here kg cancels out, and Kelvin cancelled out. So we have, okay, so it's actually joule per second per meter cube, which is essentially watt, isn't it? So what is?
So it is like we are telling how much heat added per unit volume.
Per unit volume
per second, like heat influx, like power, like heat energy, like momentum.
Yeah.
You have force per unit area, right? In momentum you have
Right.
usually stress, which is force per unit area. I think so. In that similar way, you have heat energy added per unit volume per time. That's what like kind of power. And
No, that's exactly, you're right. Yeah. Okay, so now let's define that. We'll be solving this problem. Let's solve this problem. In say 2D. Then in that case, x vector is nothing but x comma y, right?
Okay.
Isn't it, as an ordered set of x comma y?
Yeah.
And then even temperature will be a function of x, y, and t as a generic function, right? So isn't it? So this is how we are trying to do. So as per what we had learned from the basics of FEM, right? Our goal is to determine, weak form.
Yeah.
Isn't it? So that's how we work here. So ideally, what we would have done is we would have taken rho Cp partial T by partial T, and then taken this to be is equal to kappa. Then this will also be Laplacian of T plus Q, right? Isn't it? Sometimes we would prefer to call this Q dot. The reason is because it indicates per unit time, right? So that is a better way. So it actually tells us how much energy we are pumping into the system per unit time, right? So it's better to denote this as Q dot so that it indicates it's some energy which is continuously being pumped, right? So as to not, we'll just keep it Q dot. So what we would have done is we would have just multiplied both sides by some weak function, isn't it? So we'll define. I'll just explain just very what you call like superficial knowledge, because in Phoenix the way we approach this problem is slightly different. So let's first try to understand the traditional way of doing this. So we first define the set of admissible functions, which will contain all those functions. Say U is an element of, say, C, as we discussed last time, L2 functions, such that U of at omega is equal to U D, right? This is the what we are looking at, isn't it? So all those functions which happen to be of this form, which with this boundary conditions ud on omega the sum. So this is what we are looking at ideally. Right?
Yeah, because
Or maybe the other way
it
is to be
involves
more.
it involves double derivative. You need L2. Yeah.
Actually, the more generic way would be to also incorporate time because we also want to have time. So say it will be this one 0 comma t. So it's like because we are dealing with transient problem, right? So it should be an ordered pair such that it should be at every point also in the time. So omega cross is it just gives us what do you call the domain at every at every instant, right? It should still be L2 continuous. So that's what it implies here. And this should just have u of ud, and this, as we recall, can be a function of omega comma t, omega or rather xy comma t, right? This is equal to, so this is the admissible set for S, admissible set, and then the set for test function space, or what we call as the variational space. Test function or variational space. In that we'll have say v is equal to all those functions v, and here we need not have to be, because the thing is in test functions what we do is we assume that the system is in one particular configuration, right? One particular instant in time, and then we are perturbing it. So it's as if we are trying to take minor variations about some time. So what we do as per classical mechanics is we don't consider the variations to be a function of time because they are only by fundamentally it implies it's virtual in nature, right? You understand?
Okay.
When we so virtual in nature means okay, I'll just connect it to mechanics first so that it's easy to understand. Say you have some configuration, right? Some configurations applying some bodies, some forces on this body of mass m, right? And then when we are trying to say use this virtual work principle, we say that okay, this system is already balanced, totally balanced. However, we want to say that that the system is, if we apply infinitesimal perturbations. So say along each direction we apply certain what you call virtual displacement. That's why I'm using this delta here. Then it still should be work should be zero. I mean, it will be right if we say multiply both sides or say, I don't know whether I'm making sense, man. Let me just go slow here. So you start. So say this body is in static equilibrium such that the net force isn't the effective force is zero. That you got right.
Yeah.
Now, if we multiply it with certain for all forces, if we multiply it by certain virtual displacement. So virtual displacement means we are just theoretically applying on the body theoretically. We are not actually applying because we can never have that the work will be zero, right? So that's why we say that we want to have we are multiplying with certain virtual displacements such that the work is still zero. Because if, on both sides, if you multiply with delta r, right, this side also delta r, but zero multiplied by delta r, it's still zero, right?
Yeah.
So this is what we call as the virtual work principle. If we extend it, this was a static problem. Now see if it's a dynamic problem, then we even consider the dynamic forces, dynamic or what we call the inertial forces, right? Inertia forces is also considered some side of some type of force. So it also goes in summation on the left hand side here. So it even that inertia for mx double dot that also goes, but it will be negative in sign, but it will also go as a sum of this because it's like we cast even the dynamic problem in a form that it appears to be static in nature, because it's as if what would have been because what would have I mean as a body accelerates it is what you call it faces this it undergoes this inertia forces, right? So that inertia force has always the tendency to oppose the direction of motion. I hope I hope you are following
Yeah,
me.
yeah.
Yeah. So inertia, because of by virtue, what how we define inertia, right? So inertia is defined as the tendency of body to not go from the state of rest or motion, right?
Yep.
Isn't it? So to always try to what you call resist that state to which it's being forced to. So that's the reason it will be negative in nature. So it goes as some sort of force so that the virtual work is still applicable. However, the very virtual work, that virtual displacements that we give to the system are always independent of time. The reason is because we just apply a displacement which is not, which is what you call, which does not change with time. It just acts at an instant, at just some time t, and then it just acts during that time. So it will be independent of time if you are following me.
Yeah.
It's as if, yeah, it's between t and t plus delta t. So say we are considering the body or the state of the body at t, and then applying some virtual load just at this point. So, and between this interval, so during this interval, our delta R is not taken, it just happens to be dependent on the space. It will not depend on time. So that's just what you call the background of why these variations are always considered independent of time. And maybe next time I'll come with a better explanation when this is like too foggy.
It's okay, dude. But I
Yeah,
get it. I understand. I mean, अभी तो
yeah,
variation अभी time में लो. I mean, you can. I
yes,
mean, people do research. That's what research is. क्या होगा? We'll get some better optimization technique. एक problem है
yeah,
वहाँ पे भी have a problem. Okay, time variation so you take, then you get a better approximation. That's
yeah.
what we do know. So rather than
Ha ha
approximate it at some point, you approximate it at other point, like vertices में, edges में, center में,
ha ha
sometimes
ha.
it's process में.
Yeah,
ठीक
yeah.
है.
Now for variation space, we take all those functions which happens to have a value 0 on all the boundaries, on the boundary. Because the thing is, on the boundary, the temperature is prescribed, right? So we cannot allow any variation. So that's why all the variation is 0 on the boundaries. And it will not be a function of t, sorry. It will not be function. It will just be function. It's always defined from the current configuration. I mean, at every instant, that's it. So this is how you would have defined ideally. So then our process would have been to say del by del t, then multiplied by some variation, say, let me take it to be, say, some v only, and then integrate it over the domain d omega, integrate it over the domain is equal to, even on this left hand, right hand side, is the same thing, kappa t, and then, right, kappa t, then v plus likewise omega q dot v. And then we would have done integration by parts for here, integration by parts, and applied the boundary conditions. And we would have constructed what we call a weak form. And I mean, then that would be, then we have substituted all these expansions and then form a matrix system. So this is the traditional way. But for Phoenix, it approaches slightly different way, traditional form, right? This is the traditional form. But Phoenix does it slightly in a different form. So let's also try to study how to do it in Phoenix. How to implement Phoenix. So it's slightly different. So what Phoenix wants us to do is, given that once we have our equation, right? So kappa Laplacian of t plus q dot, isn't it? Once we have this, then Phoenix would want us to first discretize in time. The step is,
Okay.
or maybe first step, or say the step one.
The t plus. But that's
Yeah,
how you
first.
should do the. Hey, wait, but why were you multiplying the? You took time ka case hai. Why are you multiplying the variation to the left hand side?
No, we can apply anywhere because this variation is independent of time.
That is right, but yeah, that's I'm surprised actually. I have a question here, right here. Like
Huh.
first, I think we should do what we should do is you should discuss this time like t equal to t previous plus.
Yeah.
Then
So
you'll only take variation of the right hand side, and right hand side you'll convert that Poisson thing into some like FEM or variation formulation. That's what I think you should do. But let us
yeah,
see
yeah,
what
but
Phoenix does.
yeah, in traditional way, what we used to do exactly actually is that we first multiply and then
But time,
it
Hena Krishna, I think Phoenix is the right way. No, even you go not just
no,
Phoenix. I think
no.
that's how you should do the time problems.
Yeah, yeah. Actually, let me just explain once, right? I mean,
Yeah.
yeah, it's just
No, no,
like
no,
what.
wait. You go ahead with Phoenix, then I will see. Let's
Okay,
go ahead with
so
Phoenix.
here let me just tell you the philosophy. Then I think it will be very clearly understand.
Yeah.
Yeah, what we do in traditional approaches, we have this PD, we convert into ODE by using finite element method. So ODE in
ODE.
time.
Yeah.
This is the traditional approach.
Okay.
I have seen, I mean, in what I have seen, I have learned in all these books by Hughes, right? So he always does this, that we have PD, use FEM for spatial discretization, then convert into OD in time. So it will become set of OD system, set of OD equations in time. Then we use all those Newmark beta method and all those to integrate. That is one approach,
Okay.
which is very much used. And since I don't know about how ANSYS or any other commercial softwares implement it, right? So maybe
No,
I'm
no.
not in. Yeah,
I am okay. That's fine. Okay.
yeah, yeah. So what since for Phoenix, I just came to know so that so here what they do is they first determine or not determine. They first discretize what you call the term, the transient term using some method, some time integration method.
तुम बोलो ना क्या है. So I think we can go for like I think the best way to do is Euler. Take Euler Tn plus 1 minus Tn by delta T, right?
Yeah, yeah. For the sake of stability and all that considerations, right? Let's take
Yeah.
backward Euler scheme, which is the simplest one.
Yeah, I mean when I say Tn plus 1, I mean I know Tn and I'm trying to compute Tn plus 1. So
Yeah, so that would be like forward stepping, right? So here what we want to do is we want to have in terms of backward, so that it's for just for this from the stability what do you call requirement. You understand, right? It's just for the stability sake.
yeah, I
Yeah.
understand. I understand. So
So what
also
we do
this
is
this no this depending on how you step now there is this Riemann may you have front propagating, back propagating, this all kind of shit.
yeah, yeah,
I don't know
exactly.
what
Yeah.
this kind of sticking in sense. I don't because I don't have much experience with conventional CFD which I had, but yeah.
So the issue, what happens there, right? So the issue, what happened is that this Riemann solvers and all, right? They are used only in situations where there can be discontinuities. Then we would like to have all those that approaches, but I mean I need to still look into that. It has been quite some time. Yeah. But for today, since you'll be using backward Euler scheme. So what we can do is we can even simplify this equation to in a better in a different manner, right? Since we know that rho and Cp are usually taken to be constant, rho and Cp. So what we'll do is let's just divide throughout by rho by Cp. So
Yeah.
this becomes K by.
But I have one more question, dude. Why are we even doing partial derivative of time with capital T? Because I know T is a function of like many variables. Doesn't matter, right? Even if you take like full differential, like small d by dt. You understand? Do you agree?
Okay, so what I'm here, what we are doing is we are considering that it's some sort of just local, what you call some local heating. We are not considering anything which is flowing. As a further part in this, what you call in the set of lectures, they actually do something they actually solve it along with the momentum equation. So to it become then we are solving it's as if we are solving energy equation along with the Navier-Stokes equation. But for now, just to implement in Phoenix, right, we are only looking at say heat transfer in a solid medium. So in that case, there won't be any convection, right? No, I mean no. No convection means that there won't be any advection, that the material won't be moving from one place to another.
Okay.
That's the reason we are not taking the material derivative as you are mentioning. We are only looking at, because in material derivative there would also have in these velocities and all, right? Then in that case it becomes partial by partial t plus some say u del t by del x plus v del t by del y. This u and v will be the velocity components along x and y direction, right? These are velocity components. But the thing is, in this case, it will be 0 because there is no advection going on. There is no velocity coming to the picture. Everything is taking place just by pure diffusion. So you clearly see that it's only diffusion which is actually helping to what do you call temperature redistribution, and then q dot is like a pumping term. So just from that aspect we are looking here, that becomes Laplacian of t plus q dot by say this will just be called rho Cp, and just for the sake, let's just call it partial t of t is equal to some alpha, isn't it? Laplacian of t plus let's just call it f. Q dot by rho Cp, we'll call it f, right? So this is our equation that we are going to solve.
Yeah.
So in Backwell-Euler scheme, we'll discretize the time term as the transient term as t n plus 1 minus t at n divided by delta t is equal to alpha Laplacian of t n plus not n plus 1 and f of n plus 1. So here is where we see this. This is like backward-Euler scheme, right? So all the what you call unknown quantities are taken to be at n plus 1 level, and non-quantities at time level n. So n indicates time level, and it can go from 0 till say t by delta t. So we'll actually first define our delta t by delta t as some sort of say this as some t by n, isn't it? Say it's like n is the number of time steps, so that's effectively that's how it will be n, isn't it? So that's like delta t is equal to t by n. N is the number of intervals or number of time steps. That is the better word. Number of time steps, and T is our final temperature. Okay, here we are confusing time and again. So what I'll do is I will also replace. Okay, let it be like this. Let it be just like here. I'll just call it as say instead of 0t, let's call of TF. Small tf indicates final time. This will be, yeah, this is fine. Yeah, so TF will be the final time, right? Just to be consistent. So here it will be TF. So this is the number of time steps. Now, once we have this, we can clearly write it as let's multiply it throughout by n plus what you call delta t. So it becomes Tn plus 1 minus Tn is equal to alpha Laplacian alpha delta t Laplacian of t n plus 1 plus fn plus 1 delta t. And this we can also write as in terms of things that we know and things that we don't know. So all the unknowns, let's pull it to the left hand side. So Tn plus 1 minus alpha delta t Laplacian of Tn plus 1. So these are the unknowns, right? Is equal to Tn
No, I think f also should be known. No, we know f value, right?
Yeah. So here, what we assume is that we are solving a linear problem. So we consider f can at best be a function of x, y, comma t. It would not be a function of temperature.
The temperature.
Yeah,
Yeah.
otherwise then it becomes a nonlinear problem.
No, it
Right
can
now,
be temperature and just linear function of temperature, right? Not orders of t. Then it will be
yeah, but in a very generic sense, right? We won't know the prior form.
Yeah. I agree. That's right.
Yeah.
That's the best thing to do, because you don't want Q to be depending on the temperature. Just Q is some heat flow coming in, bus khatam.
Right. Yes.
वहां पे कितना टेम्परेचर है उसके हिसाब से we don't want to put Q. Just Q is Q.
हाँ. So yeah, that's what we are looking at. Yeah. Okay. So coming back. So then we have, I'll just rewrite it again because this is the equation that we are going to deal with. N plus 1 minus alpha delta t, then Laplacian of Tn plus 1. This is equal to Tn plus delta t of f into f of n minus 1, n plus 1. So this is the discretized equation. Now it's like discretized in time, isn't it? Now it is it's a space. Now it has become a spatial problem, right?
Yeah.
Some sort of a
Just like
spatial
many
recursive.
previous problems we had. Looks like previous problems we had.
Yeah. So now it has become spatial, just a spatial problem. Before it was space time, now it's just a space problem with just recursive,
How would
which
we
is
match? So we compute Tn plus 1. I can take those t values, substitute in Tn value, then again redo it. Yep.
yeah, exactly. At n is equal to 0, we know t is equal to t naught, right? Isn't it? That's we know from the boundary conditions that at t is equal to 0, we'll have t is equal to t naught, right? Here. So it's like we know the initial conditions. So we'll start from here. At n is equal to 0, t is equal to t naught, which is a function of x, y. Right? Now the second step is, step 2 is, now take variational form. Now construct a variational form. Now what we do is, now we'll do all that. We'll multiply it with some weak function. Some weak function, integrate over the domain. Here also Tn plus V into d omega and omega. Now what we do is, on the left hand side, right? So let's keep one term as it is. Say this one will be just Tn plus 1 into V d omega. And this term is alpha delta t, can be taken out of the equation or out of the integral. And then we have Laplacian of Tn plus 1 into V d omega. And right hand side, let's keep it as it is. So this is the term which we are going to decompose further. Yeah, this we'll do integration by parts. So as per integration by parts, it is.
So previously we did no.
Yeah. So let's write the final result. So it will be Laplace. It will be using Green's theorem, right? So grad of t dot v at. But why should it be dot v grad of t? Will it be grad of t? Because v is our scalar, right? So we cannot have grad of. So it's how should we say this? So it should be Just wondering. Okay, so it should be grad of t dot some normals, right? Because since we have a boundary, right? So it will be some normal here. At every point, there will be a normal vector into v at what do you call it, omega. So what I'm doing is I'm just looking at this term right now, just this term. Then minus, then we'll actually shift one. I mean, the order of this Laplace. I mean this partial difference, this operator, right? It will reduce by 1. So it will be grad of Tn plus 1 dot grad of V. This also follows from this Green's theorem or even from Green's theorem only. Yeah. So this will go as T omega. You see what's happening here? So this is from the integration by parts. Now you'll see something going on in this term. Do you notice something? Grad of T dot N into V at partial omega. So do we know something from before?
That's at the surface, right? So V is 0, right?
Exactly, yeah. So actually this term is meaningless. It vanishes exactly to the 0.
It's like, typical FEM.
Yeah. So
Not typical
yeah.
FEM, typical mathematics.
Yeah.
Anyways,
Yeah. But what happened?
Oops.
PowerPoint.
Anyways, no worries.
Okay. Yeah. Maybe it was doing some update in the background. Okay, we were here. Yeah, so effectively what happens is this term it goes 0, right? So this term will go to be 0. So what we would have is, so this implies that it will be partial t. I mean, and this sign will become positive, right? Minus into minus plus. So we can write it as in a single, this one as Tn plus 1 into V plus alpha delta t into grad of Tn minus 1. I can just delete this now, erase this. So I have to write this as plus alpha delta of t grad of Tn plus 1 dot grad of V d omega is equal to omega Tn plus delta t Fn plus 1 into V into d omega. So this is our weak form, essentially. And you'll clearly see one more thing. I'll just write it neatly here. And then we would go to the implementation in Phoenix after this. Tn plus 1 into V plus alpha delta t grad of Tn plus 1 dot grad of V then d omega is equal to integral of Tn plus alpha, not alpha, just delta t of Fn plus 1 V d omega. Now, do you notice something here, Dinesh? Something which is going on here. Can you say something about whether this expression, is it linear or is it bilinear or is it bilinear? Say if
Bilinear
you
means
take
in temperature and
exactly
V,
in V. Yeah. It is it bilinear? Just say if
so it's like A dot B. So it's A dot B bilinear. That's all you're asking me, actually.
exactly, yeah. Even in this case, it's the same, right? This is also bilinear.
Yeah.
Say if we scale t by alpha, I mean, say t by some constant c, then that will be effectively just bringing out c and then having the original same thing, right? I hope you are on. So say if you are scaling t by something, say c into t, Then we'll have C here, one C here, and we can just, one C here. And then what we can do is we can bring out C outside. And likewise, it will also be the same for V also. So which means it's linear in both T and +1 and V. And the right hand side, you will see that it is actually it's linear. It's just linear in V. It's not bilinear now, because say if you scale T by some constant C, it won't be this. It won't. We cannot bring C outside, isn't it?
Yeah.
Because of this term.
Yep.
So it's not bilinear. And anyway, the thing is, for right hand side, we only take it to be linear in the what you call.
That is known value, no? Right now, we know how to compute it. So.
So what we know is that we can express this in terms of what in the standard form that fenicsx take, right? The bilinear form. So a Tn plus 1 comma V is equal to L of V. You can clearly see, right?
Yeah.
So which means that we have.
Yep.
You see, right? So that was the main thing here, and we are actually solving this recursively. So here also we can even for L we can just mention that it's still a function of n or something. Just let it be like that here. It's like we'll be just be iterating from n is equal to 0 to capital N minus 1. Because it just keeps on iterating. Recursively, we'll just increment. So now you will say, OK, but how do we start? So step 3, this is like we have constructed a weak form. So step 3 is to solve this problem, right? Solution technique. So what we do is at t is equal to 0 or at n is equal to 0, we have the equation will become just omega t1 into v plus there won't be this term won't be there, right? At t is equal to 0. Because we don't know anything about the grad of t. All we need something to start from. So this term won't be there. If we let's go back to our earlier equations, right? Let's try to see here. So this term here, right? Isn't it? So it means that it has started from somewhere.
Yeah, that is typical evaluation.
Yes. So it is as if we are doing so omega. So it will be t1 into v d omega is equal to omega, and this will be just t naught, which is essentially our initial conditions, t naught into v to d omega. Or we can even have say some forcing function. So it will be f1 some forcing function into v. So it's like this is how we'll set up the problem. This is at n is equal to 0. At all other n's, this equations follows. So this is also this happens to be a special case. Only a naught t1 comma v is equal to L naught v. Or you can remove L just v because this is still similar to this one. It's only the first term, only the term on the left hand side which has slightly different form. So we start with this, we solve this first, and then just solve this till n is equal to and capital N minus 1. So this is essentially our goal. This is what we have to solve. So what I did is I just typed out that lecture. I'll just share my laptop screen now.
Okay.
And we'll just go through once how he has presented this. JS Dockery is one of the main developers of Phoenix. Let's see how he has explained this. So I wanted to keep our lecture consistent with the notations he has used. So this is the problem that we are looking at. So now we can say that okay, U is what we understand as capital T. So he does that same thing here, and then you are solving equation 21. So this is our weak form, right? And then we have projection or interpolation. Since for initial condition also we need something to start from. Okay.
So A0 is the TV. So U is here, T here.
So he just attempts to solve this, but in that case, just to we also need to approximate the initial condition. This equation can be turned into variational problem, which while solving this variational, U naught becomes the L2 projection of the given value into the finite element space. The alternative is to construct U naught by just interpolating the initial value, Fine. Now let's keep it at is. So it's like this one won't contain V F1, just T naught V. Yeah. Now let's start see how he has implemented it. And actually, I have also coded it in the same. I mean, just followed the same steps. So let's see how he has done, and then we'll also run our cases, which I have coded here. I mean, just copy and paste it, so to speak. But yeah, in a form that it can be run. So what he takes is, let's now solve a more interesting problem, namely the diffusion of Gaussian Hill. We take the initial value to be this. So initial value happens to be a function of x and y. And for a is equal to 5 on a domain of 4 cross 4. It's like a square of edge length 4. For this problem, we'll use homogeneous Dirichlet boundary conditions. UD is equal to 0. The first difference, okay. So what we do is, apart from importing all these files, let's start directly from where things start making sense. So we first define the temporal parameters. So at t is equal to 0 will be the start time, and capital T indicates the final time. And the number of steps that was chosen is 50. So based on that, we can construct our time step size. Now we'll define our mesh. So we take the number of cells along both x and y directions to be 50-50 each. And then we create this rectangle. We define our communication network, MPF communication network. Then we define the diagonal points of the rectangle.
So any problem we take, we want to convert into bilinear form, is it?
Yeah, exactly.
Then
so that is essentially how it works.
Like use Phoenix and enjoy.
But however, we must mind that this bilinear only is valid for a linear problem. For nonlinear problem, then we have to use nonlinear solver here.
I think provided this induction or introduction, we can look at any Phoenix software which deals with any kind of problem, such as fluid circuit interaction. As we can see that, okay, let's just see where is the bilinear form and see how he's doing it, and just try to understand how he's getting this bilinear form in the first place. Right?
Yeah, so at the very outset, yeah, we must be just mindful that bilinear is a quantity which is associated only with a linear problem.
Okay.
So we cannot have bilinear problem for all sorts of problems. It's only for a very special cause of problem called linear. That's the only way we can have bilinearity. For nonlinear problems, we cannot have. We will just have linearity in the test function, but not linearity in the trial function, because it becomes a complex expression of the trial function, right? So that's the reason. Then we can no longer cast it as a bilinear problem. Okay. So once we have defined the domain here with mesh cell type to be triangle, then we have defined our function space. Fem.function space is domain, comma, we have considered Lagrange what you call basis functions of first degree, which is just the simplest basis functions. So note that we have used a much than before to resolve features. Okay, this is not. So we also easily update the initial boundary conditions. Instead of using a class to define the initial condition, we simply use a function. These are just nitties and gritties. So we have defined initial condition, which takes x. X is nothing but our spatial coordinate. It is actually a vector. And then a is equal to 5. Then we are just coding this thing here, question 26. Now we define un, which is the value of u at time level n, right? Is equal to fem.function, and it also belongs to the same function class, which is capital V. And then we have prescribed the name that u of underscore n dot name is equal to un. And then also we are interpolating this function here. This function we are interpolating onto this function space. So this is, yeah, that is because of this being so high level language, right? Python being so high level language, that we give function as an argument, and then it knows how to take, it will just pass every what you call coordinate within this domain, and then it will just populate UN. This high level language. So it's like we are interpolating this function, or essentially we are projecting this function onto this function space. I hope you are following. This is you understand, right? This part, this thing here.
Yep.
Yeah. So it's as if we have an initial condition, and we want to construct this value at every point in this domain. So yeah,
Okay.
what will it? This is like a mapping. It takes every what you call position vectors in the domain, and then lets it go through this function, then obtains the value and fills that particular location of UN with that value, and then just keeps on. Yeah. Now we create the boundary conditions, and here they have uses some topology approach. So we first find the topology of the domain. So the topology here indicates that since we are solving a 2D problem, so this argument domain.topology.dim means dimension, it will be 3, it will be 2. So 2 minus 1 is 1. So for the boundary conditions, the topological dimension is 1 because they happens to be just one edge, right? So that is just 1D. Before from surface, we are extracting the edges. So that's what we are doing. So boundary facets is equal to mesh.locate entities boundary. So these are to locate all those faces which appear on the boundary. And the domain, we are passing domain and then passing the F dimension, that the topological dimension. And then we are defining this anonymous function here, which just tries to what do you call populate this boundary facets with all those with x dot shape 1, and then it just what do you call extracts all the boundary facets. Now what we do is, now we apply Dirichlet boundary conditions, and as per the Dirichlet boundary conditions, we are going to apply a value 0. So petc dot scalar type 0 here. So 0 is the argument here. So we are applying value of 0 to all those degrees of freedom which are on the boundaries. So this is what this command does here. F dot locate locate underscore degrees of freedom topological. So it takes the function space, the fdim, and also the boundary facets, and then determine all the boundary conditions, all those degrees of freedom, and then inserts value of 0 at all those locations. Actually, yeah, if you keep regularly talking about this, right, then it starts making sense. But if we keep some radical from one discussion to another, right? These things are very easy to forget, like the way they have coded it. Yeah. But once we get used to it, then it starts making quite much simpler, because this facets approach, right? Trying to determine entities from the boundary. This can be done even for an arbitrary shape also. And if you want to do some matching, say we'll only take x is equal to 0 faces. So there it's like we need to have some simple shapes where we can do all that. But for an arbitrary shape geometry, then this is the way to go, that we locate all those entities which are on the boundary. So they actually what Phoenix does is it actually marks all those boundaries with certain markers. So using this, we are able to get those markers. We are able to locate having certain markers, and then we are actually able to obtain the boundary facets. So all those faces and all which lies on the boundary, that we are able to collect. Then we are actually using this function locate degrees of freedom. Then we are able to determine, okay, which degrees of freedom in that global matrix, right? Which degrees of freedom should be will that particular facet have? So this is what we do. We are able to locate that. Once that is done, we are able to what you call provide the value of 0. So that is the general step here. Now, so the time dependent output. So to visualize the solution in external problems such as ParaView, we create an XDMF file which we can store multiple solutions in. So this is the file that they recommend. This file format we need to save our results. The main advantage with an XDMF file is that we only need to store the mesh once and can append multiple solutions to the same grid, which reduces the storage space. So that is what they are saying about the XDMF file.
Yeah. Same file. Yeah, that's some output. It's good. At least we know something HTML file exists. And
yeah. So the first argument to the XDMFL file is which communicators should be used to store the data. So here we are seeing that now we are the file writer is implemented in the class called IO. So IO is input output in fenicsx package. Then we prescribe the which communication networks. It's like domain.communication network, the file name, and then the write mode. Sorry, the mode in which so we are writing. Then we first write the mesh xdmf.write mesh domain. Now we define the solution variable and interpolate initial solution for visualization in Paraview. So UH is equal to fem.function. We are first defining the function, then taking UH.name is equal to UH. And then we are interpolating, which is UH.interpolating the same initial condition on this, and then we are able to write it. And recall that T was initialized to be 0. So it will mark it as 0. That solution file. Now we come to variational problem and solver. As in the previous, okay, fine. So here what you do is we first have to define the trial function and then the test function. And since we are quite well aware with Phoenix with Python, right? So this you clearly understand. So U is the trial function and V is the test function. And then here they have taken a constant forcing, so constant forcing term for. So f is equal to fem.constant, define the domain, and they have not taken any forcing function. So petsy.scalar type is 0. I mean, so 0 value they have not taken. So for our cases, our goal will be to extend. We'll have some generic or some other what do you call non-trivial forcing function. Then we have A is equal to, now just clearly see here what's going on. The way we had defined, right? Okay. So A is equal to U into V into UFL.dx. So it's like they have just broken our integral. So and then plus for the other term, it was we had written alpha into dt into UFL.dot, because since we are taking dot product, right? So UFL.grad U, comma UFL.grad V into UFL.dx. So this is our this is the bilinear form.
Which we wrote previously as well.
Yeah, and for the linear form, you have U underscore N, which is the results for the previous case, plus dt into F into V is our test function into UFL.dx. See how nicely we are able to define the variational problem. Now we are preparing the linear algebra structures for time-dependent problems. So this is the crux here. These are some things which we really need to understand it better. So we know that even if U underscore N is time-dependent, we will reuse the same function for F and U at every time step, because that's how we are going to increment, right? Or say advance in time. We therefore call dolphin.fem.form to generate assembly kernels for the matrix and vector. To be honest, I have not understood this clearly. So it's like it will take some time to understand what we mean by fem.form. At best, we can understand is they are just prescribing these as some what we call terms which can be evaluated later. So that's why we have some certain, it's like they have just kept this, what we call, kept the expressions and stored in bilinear underscore form. So we are not solving anything. We are just collecting or gathering this the expression and storing into some other framework. So we observe that the left hand side of the system, the matrix A, it does not change from one time step to another, right? Okay. Thus, we only need to assemble it once. This you clearly understand. So because this is not going to change. The expression is not going to change.
Right. Just the values, of course.
Yeah, the values will change, but the expression overall will remain as it is.
Yeah, symbolic expression is same. Yeah.
Yeah, symbolically it will remain. Yeah. And thus we only need to assemble it once. We'll only need to assemble it once. However, the right hand side, which is dependent on the previous time step, we have to assemble it every time step. Because after assembling, right?
Okay. Actually, left hand mean there is no like U is something to compute. V's तो हमेशा same होता है, dx is same
हाँ,
है, and similarly dot b same. But right hand में you have to again, like, you have to create
update.
L
Yeah,
value
keep on
all the time
updating
because it
this.
has UN. Yes, UN is updated.
Yeah, yeah,
Now I see. Now I see what it means.
yeah,
Yeah.
yeah. So, and it's done in a very high level language. So yeah. But the good thing is it's
Because
within just within this how much is being done at the back end, right? So we have to assemble it every time step. And you know that since it's a linear problem, the matrix A is fixed. Once we assemble, it's a fixed matrix. So that's why.
yeah.
So therefore, we only need to create B based on L, which we will reuse at every time step. So A is equal to assemble matrix bilinear form, comma, BC is equal to BC. So we are assembling the matrix, giving the bilinear form BC is equal to BC, and then A dot assemble, we are assembling it. And B is equal to create vector linear form. So for the first time, this is what we are doing. We are just B is equal to create a vector linear form. Now, as we have already assembled A into the matrix A, we can no longer use the dolphin.fem.petsy.linear problem class to solve the problem, because using this function, we just have to prescribe the bilinear form. So AUV is equal to LV. If you give to this linear problem, this is the last time we had used this only, just to show you. In the beam axial vibration problem, right? This is the solver we had used. See here, this, right? This one. So we had used dolphin.fem.petsy.linear problem, and then we had prescribed the bilinear form, AL.
Yeah.
But now we are not doing that. We have already assembled it because we don't want this thing to be assembled again and again. So just to for computational cost reasons, and also at the sake of for not repeating something,
Yeah.
we have just assembled it. And now we create a linear algebra solver using PETSI and assign the matrix A to the solver and choose the solution strategy.
Okay.
So what we are doing is solver is equal to PETSI.ksp. This is like some Krylov subspace approach, I believe. Dot create domain.com. Using that domain communication, we are able to create the solver. Then we are solver.set of. Actually, the thing is, Dinesh, we need to also review one's PETSI library.
We should. I am
Yeah.
interested in that. Very much interested in that.
Okay, so what we do is next in our next discussion, let's take up PETSI library now.
Yeah.
Yeah, because I think let's just take just as a side digression, PETSI for this one, right? I think there is the library that we. Isn't this the library that important?
Typical linear problems in engineering
हाँ
or science में,
हाँ
and we can review some linear algebra. Review as a not too much, just 20 minutes. कि क्या problem
हाँ
है, ax equal to b, वो solve करना है. Okay.
right.
We will write that simple problem and we'll see how PETSI does it and how, like.
I think that is a nice option, nice way actually. Yeah, that way we'll also learn all this. Yeah. See, right, introduction to PETSI. So what we are doing is KSP, right? So this is like a KSP is this Krylov subspace methods. So yeah, we need to go through this PETSI library. This is really useful for other tasks also, right? So we have created this solver, then set operators A, and then we have set type, which is PETSI.ksp.type.pre only means maybe some preconditional. This language is specifically from PETSI library, so I think we need to go there and look it up. And then we get PC means preconditioner, and then we have set type to be LU preconditioner, which is LU factorization. We are using it as a preconditioner, and the reason is you will ask is, but what is preconditioner? So preconditioner is a matrix which we say if we are given some say AX is equal to B system, right? Say AX is equal to B, isn't it?
Yeah.
So say if the condition number of A is very poor, if it's very close to 0 or very low, so it means that our convergence will be really very slow. No, sorry, it's not the other. It's the other way around. If the condition number of A is very high, condition number of a square matrix is defined as the ratio of the largest eigenvalue divided by the ratio of lowest eigenvalue. Now, if the matrix is singular, what will be the lowest eigenvalue? 0.
Yeah.
So condition number is infinity. At the same
Yeah.
time, and
Yeah.
if the matrix A is near singular, that means that the lowest eigenvalue will be very close to 0. Even then, in that case, the condition number is going to be very high. So the higher the condition number, the slower the system converges. You understand, right? Higher condition number. And when you talk about ill condition matrix, right? Ill condition of a matrix means the condition number of the matrix is very high.
Yeah.
Or it's near singular. So near singularity of a matrix is very much related to the time it will the convergence efforts it requires for the solution to converge. That's how they are linked. So what we would want to do is why don't we artificially change the condition number? Effectively, in that sense, effectively change the condition number so as to make the matrix to be able to solve faster or with fewer iterations.
Okay.
So that is the goal of preconditioner. So what we do is we multiply both sides by some, say, P.
Okay.
So it will be PAX is equal to PB. And P is a matrix. And based on like it takes quite it requires extensive we have to hit and trial to understand which sort of preconditioner we can use. So it should be as if P into A actually reduces the condition number of A.
Okay.
So if the condition number was say 1 lakh, something like that, say after P into A, the condition number of PA matrix,
But
see if it becomes.
does doing that, actually, are we solving the same? Or that's what we will look into it. We look into like it'll be fun to look at. Yeah.
Yeah. So that is, I just want to give you the overall philosophy. So it's once you have P into A, the condition number will be such that it will be drastically reduced. But the thing is, it's not always guaranteed. Like you cannot multiply by any precondition and reduce the this condition number. No, it requires certain analysis just to see the structure of matrix A, and also takes a lot of experience to identify the proper preconditioner. Once we have used the preconditioner, so we can drastically reduce the preconditioner to some say reasonable value, say 1000. So then our convergence will be much faster. In general, some of the widely used preconditioners are LU factorization. I mean, these are some of the widely used, which are because of its very simple nature. But for specific, we can have specialized preconditioners such as Jacobi preconditioners. There are a lot of other preconditioners. So here they have used LU factorization as one way. Now, once we have defined preconditioner, now let's skip this part. This part has been creating lots of issues using PyVista. I tried today also. It was even on Linux. It was not working. So we'll skip this part since we can anyway analyze things in what you call in ParaView, so no issue. Now we can directly jump here, updating the solution and right hand side per time step. So to be able to solve the variational problem at each time step, we have to assemble the right hand side and apply the boundary conditions before calling solver.solve b and comma uh.vector. We start by resetting the values in B because we need to reset the values in B every time, right? Because it has to be updated every time. The next step is to assemble the vector calling dolphin.fem.petsy.assemble_vector b comma l. L is the linear form, which means that we are assembling the linear for LV into the vector B. Note that we do not supply the boundary conditions for assembly as opposed to the left hand side. This is because we want to use lifting to apply the boundary conditions, which preserves symmetry of the matrix A if the bilinear AUV is equal to AVU without Dirichlet boundary conditions. When we have applied the boundary conditions, we can solve the linear system and update values that are potentially shared between processors. Finally, before solving to the next time step, we update the solution at the previous time step to the solution at this time step. So many things will be clear as we read, as we dig deeper into this Dolphin, this Phoenix library, right? So for today, what we are doing, for now, what we are doing is, now let's start iterating our time in, I mean, just marching in time. So for I in range num steps, t is equal to t plus delta t. Then we update the right hand side reusing the initial vector. So with b dot local form as loc b, we have loc b dot underscore b dot set 0. So what does b dot local form do is it gives us is as a vector form of b, because the way Phoenix store B is, they won't store as just an array. It will contain many other information also. You know, right? I mean, with all these sophisticated packages, they won't store B as just a vector. They will store in some other data what you call data
Correct.
type.
If you look at SciPy, SciPy
Yeah.
Python
Ha, ha, ha.
has something similar. I remember, and it is, yeah, it is. That's how you should do it. Yeah.
Yes, because these are objects of some classes, right?
Yeah.
And but with dot local form, what we are able to do is we are able to get the vector form of B. So then we are setting it to be with value 0. And then now we are assembling the vector based on the linear form, which we had stored as some formed language, right? So some of this through some assembly kernel. Assembly kernel is something like we store in some sort of an abstract form. So once we do this, and then linear form, it also knows that L will depend on U, and so it will automatically go all the way. It will retrospectively, what you call, just here they will just modify it and then assemble a vector B. Now we are applying some lifting. This we actually need to understand. I'm not very much like it's going too much, but yeah, we'll have to gradually understand what is the concept of lifting. That they want to say that they still want to preserve some of the symmetricity of the matrix. So lifting B, comma, bilinear form, comma, then giving the boundary conditions. Then b dot ghost update adv is equal to pets insert mode add values. This I don't know. I really need to see. Mode is equal to petsy dot scatter mode dot reverse. These are some high level language going on. Then we are set bc is equal to set bc b and all the boundary conditions. Now we are solving the linear problem. So solver dot solve b uh dot vector. So since we had already prescribed this operator, right? Operator was a, isn't it here? So it already knows about A. Now we are giving B, and then the results will be stored in UH dot vector. And then UH dot X dot scatter forward. This I don't know what it's doing. Then we are updating the solution at previous time step using the current time step, using this result. So U underscore N dot X dot array is equal to UH dot X dot array. So they have stored. Now we are writing the solution to the file UH with T is just our indicator or marker, and this for this the rest of the things we can just ignore because we are not using any plotter right now. And then plotter dot close, and then this we have also closed the xdmf pack, that instance that was open.
Yeah.
Now what I'll do is I'll just run it here. Let's run this thing.
Okay.
Run all. It's able to run very nicely. Save it. And then also let me start initiate one para view. You need to visualize this. File. Okay, don't worry. I have two versions of Paravi. I have one Paravi.
Okay.
I have one Paravi install even on Windows. So if this takes too much of time, we can just use that Windows version also. Oh, come on, I think this will take much longer. So why not I use Windows? Yeah. This Paravi is the Ubuntu version. So I have launched Windows version. Let's see how long it takes. Yeah, it's found. Okay. So this is the Windows version. So here it should be faster. Open. Then we can have say OneDrive. So here, OneDrive. So this is the one, diffusion.xdmf. So let's use some reader, apply. See?
Yeah.
So let's zoom in. And then see, let's go frame by frame, see. Next frame, see, so this is how it's diffusing fast. Let me rescale to our all time steps, rescale. So this is our values. Now let's just plot one by one. So it's diffusing very fast, right? Yes, after some time. So that is, yeah, just for visualizing. So this is what it is.
Okay.
And so next time what we'll do is we'll try to expand it further such that we'll take some non-trivial forcing function.
Yeah. I think that's.
And also, I think, yeah.
Yeah. Go ahead.
And also we should start, let's have one session on even in that same session, we'll also talk about PETC. Yeah, I think PETC is something we should really know. So here the initial condition, I'll just yeah, so apart from that, we also, with all those models, I don't see it's worth it to discuss. So I'm just skipping it for the lectures in the lectures, right? So too much of information. So we just want to be close to them. We just want to solve this equation. And then apply certain certain different what do you call values and all.
Okay.
Different sort of heat models, right? So we'll do a few and then we'll just stick to whatever we want to discuss. Maybe I'll just stop recording so that we can chat.
Yeah.
So okay, let's meet during the next session. Stop recording.